Alrighty.
Okay, so like, if I wasn't stupid,
So today we're just going to look at some a little more complex trig equations. That's all. Okay, just a little more complex trig equations, such as this. Could be. Okay, so how might we go about solving this? Add 4 to both sides? If we add 4 to both sides, then it will no longer be equal to 0, and factoring a sign out won't be very helpful because then we can't use the zero product property, right? So if I add a 4 over, we'd have something like this. And yes, we could factor a sign out then because we do have that GCF now. But, okay, the problem here, I'll zoom in a little bit more on that. The problem though, right, is that when two things multiply to make 4, when two numbers multiply to make 4, one of those two does not have to be 4, right? So for example, I can multiply 8 and 1/2, or 2 and 2, and that would make 4, right? It's not equal to 0. 0 is the only number with the special property where if you know two numbers multiply and the answer is 0, that means one of those two numbers has to be 0. There's no way to multiply to get 0 without having 0 be one of the numbers you multiply by. So equaling 4, factoring it, what's that?
Why don't you like square root it?
Square root it? Like from at what point?
Like square root the sign squared.
Well, so in an equation, we can't just square root out of nowhere. You have to square root the entire left-hand side and square root the entire right-hand side. So we couldn't just we can't individually square root something. It has to be the entire left-hand side, entire right-hand side. Which would end up then, we would have this whole mess over here underneath the square root. Or, again, this whole mess under square root if you want to do it here. Or, I guess we could like subtract 3 sine x over, but again, it'd be 4 minus 3 sine x. So, again, the square root there is not going to quite work. So, Grant. Oh, from here to here, you're saying? So, I factored a GCF of sine of x. And that's so, like, right there. So, you can see, like, sine squared, I took a sign out of it, and that leaves a sign behind. Taking a sign out of this, it leaves a 3 behind. So.
And then can't you just minus 4?
Subtract 4 back over?
Yeah.
Could, but then we don't have a product anymore because we would have... Then we don't have a product anymore. Right, we have now a difference. It's equal to 0, but yes, Ethan, you have an idea.
This is in x squared plus cx minus c.
Yes, it's a quadratic. This is a quadratic. Yes, so we're going to factor it. Okay. So we are going to factor this thing, right? It's like sine of x instead of x, right? So we need two numbers that multiply to make what? In this case, two numbers that multiply to make -4 and add to make what? It's 3, right. We're going to multiply to make -4. We have to add to make that coefficient of 3 there. And so that's going to be plus 4 minus 1, right? Like that. And so then we will set each factor, again, two things that multiply to give us 0. So we'll set this factor equal to 0. And we'll set this factor equal to 0. And we get sine of x equals -4. And sine of x equals 1. Okay? When does sine of x equal -4? Never. Okay? When does sine of x equal 1? Pi over 2. Okay? And we'll, again, just stick for 0 to 2 pi. Okay? We'll just stick for 0 to 2 pi right here. So we have one solution, pi over 2, in this case. Of course, if we wanted to get additional solutions here, if we didn't have the limitation of 0 to 2 pi, we would add what to that pi over 2 to get more solutions? 2k pi, right? Multiples of 2 pi, integer multiples of 2 pi. So 2k pi where k is an integer, right? Exactly right. Okay, because again, sine repeats itself every 2 pi. Okay. Great. Let's do another one here together, and then I'll have you guys try one on your own. Let's do, again, same directions. We're just going to solve for x between 0 and 2 pi. Tangent x times sine squared of x minus tangent x sine x minus 2 tangent x equals 0. Okay. So there's our next little example we'll look at there. Okay. Oh, right. All right. So, Chrissy, any idea about how to start here? Okay, we're almost to that point. So it's equal to 0, so that's good, right? I see a GCF here, right? What's the GCF we can factor out here, Chrissy? So there's a tangent in every term. So let's take that tangent out first. Okay. And now, Chrissy, you're going to say we're looking for two numbers that do what? Multiply -2 and add to -1, right? It's another quadratic. We see another quadratic now. Okay, so it'll be sine of x and a sine of x here. And Chrissy, what are those two numbers? What are the two numbers that multiply -2 and add to -1? -2 and positive 1, yeah. So -2 plus 1. There you go. Okay. And now we have three things that multiply make 0, so we'll set each of these three things equal to 0. But I'm going to go ahead and just solve them, if you'll permit me to do that. Okay. So let's see here. Caitlin, do you remember when tangent of x equals 0? It does. Think about tangent in terms of sine divided by cosine, right? So tangent, if we think about tangent as being sine divided by cosine.
Doesn't it?
0.
It's 0.
Okay, so tangent will be 0 when sine is 0, because that will give your numerator 0, and that will make the whole thing 0 then. So right, sine is 0 or, well, 2 pi, but 2 pi is not in our range here. 0 and pi, 0 and pi. Okay, 0 and pi. All right. There you go. And then how about, let's see here, Molly, when does sine of x equal 2? That's right, there's no answer.
Yeah.
It's not possible, right? The biggest value that sine can be is what? 1, right? So 2, impossible. Okay. And let's go to, oh, come on, man, it's not very random. Brendan, sine of x equals -1. When's that happen? When x is?
7 pi over 6.
I don't know, it just is.
At 135.
It's 3 pi over 2.
Oh, it is?
It's 3 pi over 2, yes.
You make me question my whole
So, -1, Brendan, right? So sine is the y coordinate on the unit circle here. -1 is right here on the unit circle, and that
3
is
pi
then
over 2 is negative.
3 pi over 2.
I didn't get
Divided
you.
by 0.
That's okay. What's that?
Oh, wait, you're asking for sin, not...
Correct. This is now sine. Yeah, we have to adjust because of the different factors. Okay, and there are solutions. So 0 pi, 3 pi over 2. And again, if we want to get more solutions, what will we add to the 0 and the pi?
8 pi.
Just kidding.
Okay, yeah, so in this case, we only need to add k pi. We would only need to add k pi. Now, your answer, Caitlin, of 2k pi, I think would still work because that would end up still catching all the same values. It would still catch all the same values, so it would still be okay. But in general, right, when you talk about tangent solutions, you want to add k pi. And then what about for this solution right here, what will we add here? 2k pi, because again, sine repeats itself every 2 pi, tangent repeats itself every pi. Okay, so cool. All right, here's one for y'all to try. Okay, and I won't put you on the spot until you've had some time to think about it now. Yep. Okay, so that's 2 cosine squared x minus cosine x minus 1 equals 0. Sorry for that little doodle that bled through there, but you get the idea. Okay. Want to think about maybe like you're having trouble factoring this, think about maybe doing a change of variable. Maybe say, you know, instead of writing a cosine squared of x, maybe make that 2x squared. And instead of cosine, make it minus x. You know, if you need to see it maybe in terms of just x, do that. You know, do a change of variable maybe to make it easier for yourself. Change cosine of x out for like x or t or u. So, yeah, not quite. If you add the 1 over, then you could, but then you got to equal to 1, you need to stay equal to 0. So you want to factor this like it's a quadratic. Factor like it's a quadratic. Oh, I see what you're saying. So when you do that, do you use like that? So you're going to leave this. You're going to rewrite your middle term as negative 2 cosine x plus 1 cosine x. And then minus 1, and factor by grouping is what you want to do. Because if you were to multiply this back together, you wouldn't give you this. Cosine times cosine, what's the resolution? 2 cosine. Right? So that's 1 is 2. So negative first. So then cosine times negative 1 gives negative 1 cosine. Cosine. Say it again, sorry. So here, every term had a tangent. That's why we factor GCF. Not every term has a cosine.
I really should know that.
Yes, and now it's back to like should work out. How do you know when you use reference? Okay, want to draw your reference?
Run out to the pool in the middle of the sun, like you're doing like 100, and I had to get out halfway through it.
Oh, I see what you're saying. What is like the axes of the well, those are like, so that would be then 0, pi over 2, pi, pi over 2. Right? Like you know the positions of those things. So at that point then the coordinates are going to be some combination of 0 or 1. That's it, right? Because if you're here in the circle, that means you're at point 1 comma 0. So cosine of 0 is 1 because you're 1 on the x-axis. Sine of 0 would be 0 because you're not up or down. That makes sense. And then up here at pi over 2, cosine of pi over 2 is going to be 0 because you're on the y-axis, right? So sine of pi over 2 would be 1. 1 and so forth around. So be negatives and stuff.
And I was like this,
So yeah,
watching Little Mermaid on my computer.
between your representation circle you should be. Good.
I was like seeing Chris Paul say that, and then I switched back to the back, switch again, so I'll switch again.
Mr. Williams.
Yes.
David says hi. Medina.
Oh, say hi back. Is he staying out of trouble?
Sure. Yeah, he is.
Really?
Yeah.
That's good to hear. That is good to hear. Okay. Let's go to Maddie G. Were you able to get a factor here?
Yes.
Okay, what did factor to be?
Cos of x minus 1.
Cos x minus 1.
And
2 cos x plus 1. All right, let's see here. 2 cos x times cos x is going to be 2 cosine squared. Minus 2 plus 1 will be then the minus 1 there. And then minus 1 times plus 1, minus 1. Looks good to me. Seems legit. All right, so now we set each one of those factors equal to 0. Add 1 to both sides. Cosine x equals negative 1. And Maddie G, did you get when cosine x equals negative 1? At 0? I can't do math. There we go. 0 is right. There we go. Okay. And then subtract a 1, divide by 2, we get cosine x equals negative 1/2. And Maddie G, did you get when cosine x equals negative 1/2? 5 pi, 6, 7 pi, 6. Okay. So there are your solutions.
Wait, is it not 2 pi? You could do like not included.
Correct. Yeah, so 2 pi would not, I wouldn't count it against you, for example, but it is, yeah, it's redundant if you already have the 0 there, basically. Okay? And of course, right, if we didn't have that limitation here, we would add 2k pi to this, we would add 2k pi to this, we would add 2k pi to this, where k is an integer. Okay?
I have a question. Isn't it pi over third root, not pi over 6 for the cosine?
Well, we're trying to see when cosine of x
Yeah,
is...
I know, but that's the adjacent. Cosine is.
Yeah.
Oh, she's right. It is over 3. Cos of 5 pi over 6 is root 3 over 2. Sorry. No, I just noticed that. I was like, wait a minute.
2 pi thirds.
Yeah.
2 pi thirds.
Okay. Thank you for saying something.
You
Yes,
didn't notice.
I didn't. But typically I feel like, well, I understand, well, yeah, I'm not going to blame you guys. I didn't notice, you're right. Okay.
So we get the x and y mixed up for the 60, 30, 90, 100.
It is. So,
It's like, where's the right angle?
questions on this?
Alright, babe, assigned to you. You get it.
Is that 3 theta or 30?
3 theta. Okay. Now we're going to twist things up a little bit.
Again.
And put, you guys are too comfortable now. We have to twist it up more, okay? So, cosine 3 theta.
Concept in whatsoever.
All right. Well, we're gonna continue then with that. So cosine 3 theta equals 1/2. All right. Cosine 3 theta equals 1/2. So the 3 is inside the cosine, in front of our variable theta there, but inside the cosine. What does a 3 in front of the theta, but inside the cosine? What's that going to affect about cosine?
Stretch.
So which stretch? One of them.
I have notes on
Is the horizontal stretch, right? This is going to affect the period of cosine as well. All right, it's going to horizontally, I think, shrink in this case, right? Divided by 3. Okay, so our solutions will also be shrunk as well. Okay, it'll be stretched as well. So how do we account for this? Well, one way you can kind of do this is treat this.
Wouldn't it be the b?
Yes, it's like, yep, exactly right. Treat this like a regular cosine, and we're going to do that by doing a change of variables here. So just like you could have used a change of variables for solving those quadratics and stuff like that, we're going to do a quick change of variables. and just rewrite the problem as cosine of u equals 1/2. Okay? And now to solve this problem, not that hard, right? We just got to figure out when cosine, or for what angles, when you take the cosine of it, you get 1/2. So cosine of what? Cosine of what angles give you, bless you, positive 1/2? Pi over 3 and 5 pi over 3. Okay? And so if I wanted to find additional solutions here, by the way, if I wanted to find additional solutions to these, what would I add to these two numbers? 2k pi, right? Because this is just for cosine. This is just for plain old cosine here we're talking about with the u. And so we're going to add, we'd add 2k pi, k is an integer kind of thing, right? And I don't feel like writing out the sentence, so I'm just going to use the symbols, okay? There it is. Okay? That's if we were just talking about plain old cosine here. Yes? I'm getting to that in just a second. We're almost done. We're not quite done because I didn't want to solve for u, I want to solve for theta. So I've solved for u here, but I can replace u with what? U is equivalent to 3 theta, right? So I'm just going to replace the u with the 3 theta.
5 by 3.
And you got it, exactly right. We want to get the theta by itself, so we'll just divide 3 theta by 3. And of course that means we have to divide the other side by 3 as well. So everything divides by 3, right? So divide everything by 3. Here we get theta equals, pi over 9. 5 pi over 9. And then if we want to get additional solutions, we're not going to add 2k pi. We're going to add 2k pi thirds. Okay? That period diminishes, shrinks as well. Bless you.
Thank you.
Okay? With pre-calculus? Something else? Okay. Patience is a virtue. Okay. So, if our directions were still to if our solutions were still for theta between 0 and 2 pi, we're not quite done yet. So let me just get up to this point. Any questions up to this point? Any questions up to this point? Makes sense pretty much the whole way through here? Yes? Okay. Kind of? Okay. So we aren't quite done if we're trying to solve for all angles theta between 0 and 2 pi, because we said here we can add integer multiples of 2 pi over 3. Well, if I add 2 pi over 3 to pi over 9, which really adding 2 pi over 3 is the same thing as adding what? 6 pi over 9. I'll put the k there, I guess, because I forgot to put it. Right? 2/3 is the same thing as 6/9. If I add 6 pi over 9 to pi over 9, I'm now at 7 pi over 9. Right? If I add 6 pi over 9 to 1 pi over 9, I get 7 pi over 9. Is that still between 0 and 2 pi? It is.
But not with the other one.
Well, let's see. So what's 6 pi over 9 plus 5 pi over 9? 11 pi over 9. Is that still between 0 and 2 pi? Because what would 2 pi be in terms of ninths? 2 pi is 18 pi over 9. So 11 pi over 9 would absolutely still work.
And so would 17.
And so then we're going to add 6 to the 7 again. We get 13 pi over 9. And add 6 to that, we'll get 17 pi over 9. And then finally we're done, because if I add 6 to that, I'll be at 19 pi over 9. And that's no longer within our range. So in fact, we end up with 6 solutions there. 6 solutions. Okay? Because those all fit between 0 and 2 pi. That's interesting? Good. Good. All right. So this is a situation where I think, like normally the problems where we limit the range, limit the solutions between 0 and 2 pi, those are the easier ones because you just then come up with stuff on the unit circle. You don't have to worry about plus 2k pi or plus k pi if you're doing the tangent or cotangent. Here though, Now, with the change in the period, when you limit the domain, I think these are a little bit harder because you got to come up with, the more solutions. If we didn't have the limitation here, if it just said solve for any theta, you could just give these two solutions, pi over 9 and 5 pi over 9, and then just say, oh, plus 2k pi over 3, and that would give you all your solutions, right? Because if I add 2k pi, or 2 pi over 3 to this, I get this, and add it again, I get this, and 2 pi over 3 plus this, it gives you all those kind of things. But here is a situation where now when we limit the answers, we actually make it harder on ourselves, I think. Or it makes it harder, I think. My opinion. Okay. Shall we do another one? Let's do it! I'll take that as a yes, even though Jenna said no. Is it the last one we're doing? Maybe. We'll see. If it's the last one yeah, sure. Potentially, yes. Okay. All right, 3 tangent of x over 2 plus 3. Is the plus 3 inside the tangent or not? No, okay? You would see parentheses around it if you did, okay? Is the x over 2 in the tangent? Yes, right? It's a single term, x over 2, so we count it all as one thing, and so it would be in the tangent. Okay. So, again, I see we've got something other than just plain old x in the tangent here. I'm going to do that let u equal x over 2 thing. Nope, you can use theta here if you prefer. Whatever. I like to leave it as like a weird variable, though. I like to use like a weird variable because that then kind of clues my brain in that, oh, we still need to make like a final substitution or something like that at the end. So, yes. We say this because with the, it's something that isn't, it's good mathematics to do it, right? Because otherwise, if it wasn't me, because I'm the one teaching you this method, so it makes sense, that when I see a u show up out of nowhere, I would understand what you're doing. But I'm trying to prepare you for an example, if you decide to take calculus or AP statistics, for example, and you're going to have someone grading your paper on that AP test that doesn't know who you are, this is good mathematics, okay? And in fact, AP graders will take off points if you don't write something like this, but you do something like this, okay? And again, if that seems weird to you or unfair or kind of intimidating, your AP teacher, if you decide to take an AP math class, will prepare you for those kind of idiosyncrasies that the graders look for. Okay? So, long story short, it's good mathematics. Okay. All right. Anywho, solve for tangent, right? So we get tangent of u equals -1. And so, when does tangent equal -1? At what angles? At 3 pi over 4 and at 7 pi over 4. Okay? And here, if we wanted to get additional solutions, we would add what? Since it's tangent, we would add
Pi.
k pi. Yep, integer multiples of pi. Okay, like so. But of course, we're not solving for u, we're trying to solve for x. So replace the u back again with the x. Okay, not divide now, we're going to multiply both sides by 2. So we get 3 pi over 2, 7 pi over 2, plus k pi, or 2k pi now, I guess. Okay. So in this case, if we were only looking for solutions between 0 and 2 pi, what would our answers be? If we were only looking for answers between 0 and 2 pi, what would our answers be? What would our solutions be? Not neither. 3 pi over 2. But only that one. Okay? So if that was the only solutions we wanted was between 0 and 2 pi, only 3 pi over 2 would work. Okay? But if we're looking for all solutions, here, if we were looking for all solutions, how should we describe those? Well, we could say 3 pi over 2 plus 2k pi, 7 pi over 2 plus 2k pi, but that's redundant because 3 pi over 2 plus 2 pi is going to give you 7 pi over 2. So in other words, all we really need to say is 3 pi over 2 plus 2k pi there. And that's sufficient. It covers the 7 pi over 2 as well. Okay. But notice, even though it was a tangent function, we're adding integer multiples of 2 pi. Why? Because tangents period, because of x over 2, it's stretched. And now tangent repeats every 2 pi because of the dividing by 2. Okay? Questions on any of that? You don't really get it? So anything in particular? Like, where do I lose you? I mean, I'm assuming you're okay down to like this point, right? Okay. So down here, you're saying? So, okay, so you're okay with getting the u equal to this, and the x over 2 is this, and then multiplying both sides by 2 to get this? All right, so you're like 90% of the way there, and that's good. So what I'm trying to say here is there's kind of like two different ways we describe our solutions, or two different ways we're asked to present our solutions. One way, we're asked keep it between 0 and 2 pi, because that's our typical kind of like unit circle stuff, and so we just like keep it between there. As a result, if I look at my solutions here, 3 pi over 2, that is between 0 and 2 pi, so I keep it. 7 pi over 2, that's greater than 2 pi, right? 7 pi over 2 is more than 4 pi over 2, so it's out. Make sense? Now, Laura, that is in a little bit of contrasting with what we had back here when I was trying to say between 0 and 2 pi. Why? Here our period stretched, so that means it like elongated, so it's longer than the normal kind of period, and so less solutions fit in there because we stretched it out between 0 and 2 pi. But here we've shrunk our period, so more solutions are going to fit between 0 and 2 pi because it's shrunk down now. So we just take that pi over 9, the 5 pi over 9. Okay, and we add more of those 6 pi over 9s until we're no longer between 0 and 2 pi. We just keep adding it, that idea. Okay, and then here for all solutions, we just start with that 1, 3 pi over 2, and we add 2k pi. If you, Laura, said 3 pi over 2 plus 2k pi and 7 pi over 2 plus 2k pi for here, that'd be okay too. It's just, it's redundant. You don't need to say both because 3 pi over 2 plus 2k pi will cover 7 pi over 2. It's going to hit that and then all the other solutions after it too. So it's encompassed all in one. Well, okay, any other questions? Okay, so I've got one more example here I can show you, or if you want to just go ahead and get started on the homework, we can do that too. But I would encourage you to get started on the homework here, okay? So, but for anyone that wants additional, an additional example, I'll do it up here at the board or something like that if you'd like.
Yes.
Okay, I can do that. But for everyone else, ready to go, homework is in the book on page 394, numbers 33, 39 to 43, 63, 91, and of course, just do the odds, please. Okay, the odds solutions are in the back of the book, so feel free to look those up if you need to. Okay. There you go.